In this video, I want to have a look at integrating trig functions. So we've already had a look at differentiating trig functions, and we know that we have these formulas on your formula sheet. So we know that sine differentiates to cos, cos differentiates to sine, minus sine, and tan differentiates to sec squared. So if we're integrating, we're going to do the reverse. So on your formula sheet, you have this. So the basic rule that we're shown here is that if we integrate sine, we're going to end up with minus cos. We integrate cos, we're going to end up with sine, and if we integrate sec squared, we're going to end up with tan. But the other bit that's in there is that if we've got a function, so instead of just having sine of x, if we've got sine of a linear function, ax plus b, then that's going to integrate to minus 1 over a cos of that same linear function. And of course, we have our constant of integration on the end as well. So as well as integrating back, so from cos to sine, we also have to divide by the derivative of that function inside the brackets. So let's have a look at some examples. On our first example, we're asked to evaluate the integral of sine 3x dx. So it's an indefinite integral, which means we are going to have our constant of integration. And because cos differentiates to minus sine, we know that sine differentiates to minus cos. But because of this 3 in here, it's actually going to be minus a third cos of 3x plus c. So that's our first example. Our second example asks us to find the integral of cos of 2x plus 3 dx. So again, we know that cos integrates to sine, and we need to divide by the derivative of this function inside. So that's going to be a half, because the derivative of this is 2. So a half sine of 2x plus 3 plus our constant. All right, our third example is going to be a definite integral. We're going to go from 0 to pi on 2 of sine x with respect to x. So because it's a definite integral, we're going to have our square brackets. Sine integrates to minus cos. We're going to have minus cos x between pi on 2 and 0. So that's going to be minus cos of pi on 2 minus cos of 0. Now, to find the value of cos pi on 2 and cos 0, we're going to need our graph of our cos function, which looks something like this. Oops, again, not very proportional, but you get the idea. So that has a period of 2 pi, which means that pi is here and pi on 2 is this value here. So this is 0. So we're going to have minus 0. And then this negative is going to become a plus, and the value of cos at 0 is 1. So all up, that's going to give us 1. Our fourth example asks us to find the definite integral between pi on 6 and pi on 3 of sec squared dx. So that's going to equal, we know that sec squared integrates to tan. So we'll have tan x of pi on 3 to pi on 6. So we'll substitute those values in. So we'll have tan of pi on 3 minus tan of pi on 6. Now to find those values, we need to use our special triangles, which are on our formula sheet. So our special triangle, pi on 3 is 60 degrees and pi on 6 is 30 degrees. So that means we need our triangle that looks something like this. So that's 60, that's 30. That's 1, 2, and root 3. So tan of pi on 3, so tan of 60 would be opposite over adjacent, so that's going to give us root 3, minus tan of 30 degrees would be 1 on root 3. Now I'm going to rationalise the denominator of this second one, so we'll have root 3 minus, you'd have to times top and bottom both by root 3, so we'd have root 3 on 3, and then if I make them have a common denominator, this would be 3 over root 3. And now, because they have a common denominator, I can simplify that into one fraction, and we would end up with 2 root 3 over 3. The last example that I want to have a look at is the integral of cot x dx. So cot x isn't one of our ones that's on our formula sheet, but we can manipulate it so that we can use our previous knowledge of integration. So we know that tan is sine on cos, and because cot is the inverse of tan, cot is going to be cos on sine. So we're going to rewrite this as the integral of cos x over sine x dx. Now, the relationship that's important to see here is that cos x is the derivative of sine x. So we have a function in the denominator and we have that function's derivative in the numerator. So that actually means this is coming back to our log integration. So that means that this, oops, changing colored pens all over the place, is going to be equal to log to the base e of sine x plus our constant. And that's because we have the derivative of this new denominator in the numerator. All right, so that's having a look at integration with trig functions.